In this lesson, we're going to look at comparing similar solids. That would be two solids like two prisms that are the exact same shape, exact same type of dimensions, but the side lengths, the areas, and the volumes are all proportional with each other. Now those ratios of the side lengths, areas, and volumes are going to be a little bit different, but they are going to still be proportional. To start this off, what we're going to do is we're going to start off with a simple conversion. This is a conversion you guys should all know, that 1 yard is equal to 3 feet. Now the question that usually gets people stumped is when you start talking about square yards. 1 square yard is equal to how many square feet? You ask an everyday person on the street, the likely answer, probably you're going to get 3, and it's actually wrong. So let's take a look at an example of why that is. We're going to use our friend here, the Rubik's Cube, just to demonstrate this example. As you can see here on the side of the Rubik's Cube, this length right here could be represented as 1 yard in our example. Or 3 feet. Either way you look at it, you got 1 yard is 3 feet. Now, on this side of the Rubik's Cube, on the white side of the Rubik's Cube, what we have here is the area of a side. That side is 1 yard by 1 yard, which makes that 1 square yard. Now, how many square feet are involved with that 1 square yard? Well, if we count them off, you have 2, 3, 4, 5, 6, 7, 8, 9. You have 9 of them. So 1 yard, or 1 square yard, is actually the equivalent of 9 square feet. So what happens there is that your ratio changes when you talk about a linear relationship, which is 1 yard to 3 feet, and you change it over to area. Now that ratio has changed from 1 to 3 for length to 1 to 9 for area. Now let's take a look at what happens with the volume. What if we were talking about 1 cubic yard? How many cubic feet would be involved with that cubic yard? So we're going to use the Rubik's Cube again. I like this example of the Rubik's Cube because it kind of shows the different layers. If we look at the top layer of this Rubik's Cube, when we're talking about volume, the entire Rubik's Cube, it's 3 by 3 by 3. That is 1 cubic yard, or 1 cubic yard by 1 cubic yard by 1 cubic yard. We can go back to our previous example here. You got your 1 yard this way, 1 yard here, yard by yard by yard. That's 1 cubic yard represented. So same thing on this one, except you can see that the layers are kind of rotated slightly. So how many cubic feet are in that cubic yard? Well, how many cubes do we have in this top layer right here? We actually have 9 represented cubic feet on that top level. Now, that top level is repeated again in the middle and on the bottom. So we got 3 levels of those 9 cubes, which gives us the total of 27 cubic feet. So if we take a look at the Rubik's Cube example with feet compared to yards, when we look at our length ratios, these are the ratios that most people are familiar with here. You have a 1 to 3 ratio. When you had an area ratio, On our example, we were strictly looking at just the side lengths. We went to a 1:9 ratio. And then when we switched it to look at a volume ratio, we ended up looking at a 1:27 ratio. Now those ratios, anytime you have a 1:3 length ratio, or you'll learn that this is also called a scale factor, that you will have an area ratio of a 1:9 and a volume ratio of 1:27. These three ratios are per se married together. They're always going to be the same ratios for the same situations. Now what you have to know to do is when you are given a length ratio, you are going to have to be able to convert it to an area ratio, or take an area ratio and convert it back to a length ratio. To take a length ratio and convert it to an area ratio, what we do is we take the length ratio and we square it. To take an area ratio and convert it back to a length ratio, the opposite of squaring would be the square root. So if we take the 1/3 and we square it, we end up with 1/9. 1/3 squared is 1/9. Square root of 1/9 takes us back to 1/3. To square root of a fraction like this, you simply take the square root of the top number, the numerator, square root of 1 is 1, and you square root the bottom number, the denominator, square root of 9 is 3. Now to get from length ratio over to volume ratio, we take that 1/3, that length ratio, and we take it to the third power. 1 to the third power is 1. 3 to the third power is 27. To go from volume ratio back to length ratio, what you have to do is you have to use a function called the cube root. Cube root is how you undo a third power. The cube root of 1/27 is 1/3. The cube root of 1 is 1. The cube root of 27 is 3. You can find the cube root key on one of my graphing calculators under the math menu. You go under the math menu and it is option number 4. So if I wanted to demonstrate here, pop out a larger display for you guys, make it a little easier to see. I'll exit out of there. We can clear that out. You could cube root by going math menu, option number 4, do your 1/27, use your right arrow key to get out of the cube root, and you can see your answer comes out as a decimal. If you don't like how that looks, when you're done typing it in like this, you could also go back to the math menu, use option number 1 after you have used that right arrow to get out of that cube root symbol, and you can turn that back into a fraction by using the turn to fraction function. So if I wanted to make a generic kind of cheat sheet type or formula sheet type relationship here between length ratio, area ratio, and volume ratio, it would look something like this. LR is going to stand for length ratio. We'll go A over B for our length ratio. We'll put an AR over here for area ratio. Our area ratio would be A squared over B squared. To get from length ratio to area ratio, you would square it. To go from area ratio back to length ratio, you would square root it. Now to go to volume ratio, we'll go VR for volume ratio. To go from length ratio to volume ratio, we would cube it. So that would make our ratio A cubed over B cubed. To go back to length ratio, we're looking at cube rooting. that volume ratio. If I were to give you a cheat sheet or something to put in your notes to symbolize the changing between length ratio, area ratio, and volume ratio, this is exactly what I would show you. If for some reason I gave you an area ratio and I asked you to change it to a volume ratio, it would be a two-step process. Area ratio to a volume ratio, first you would have to square root it, and then second you would have to cube it. You would have to take that area ratio, turn it back to a length ratio, and then convert it back to a volume ratio. Similar, if you go from volume ratio back to area ratio, if we're going from volume ratio back to area ratio, you would have to cube root it to get it back to a length ratio, and then square it to get back to that area ratio. One thing I failed to mention earlier is if you have any fractions that are not simplified, you are going to want to simplify them before you try to do any conversions, because otherwise your numbers may not square root or cube root nicely, or when you square them or cube them, you're going to get some astronomically big numbers that you don't want to deal with and are going to be wrong, because your fractions always have to be in simplest form. So in order to help you with that, simplify your fractions as soon as you write them down. Always simplify before you start any process in this unit. So let's say we have our two cubes here. You can see I got two Rubik's Cubes. One's a 3 by 3. The other is a 5 by 5. So if I wanted to take a look at my three different ratios here for these two Rubik's Cubes, my length ratio, or my scale factor, would be a 3 to 5 ratio. Side length here is 3, side length here is 5. A length ratio there would be 3 to 5. For my area ratio, if I want to convert that to an area ratio, because maybe I'm trying to find a missing area like a surface area or lateral area or something like that, my area ratio for this, I don't have to do any calculations on my cubes to find that area ratio, because all I'm going to do is take my length ratio and square it. So if I square that, that becomes 9 over 25. That's going to be my area ratio. If I wanted to go back, I could by square rooting. The square root of 9 is 3. Square root of 25 is 5. Now if I want to convert this and look at volumes, again, I am not going to find the volumes of each cube, but I am going to find the volume ratio by taking my length ratio and cubing it. 3 to the third power is 27. 5 to the third power is 125. If I wanted to go backwards, I could always cube root it. Those are my three ratios that I would be inclined to possibly use with this example of those two Rubik's Cubes, the 3 by 3 and the 5 by 5. So basically, as we work through these, there are going to be four main steps that you're going to use on most of these problems when you're trying to find a missing value. Step number one is find the given ratio. They'll either start you off with a length ratio, area ratio, or a volume ratio. Keep in mind, length takes many different forms. It could be called the scale factor, which is kind of a unique name, but it means a length ratio. Other lengths might include altitudes, perimeters, radius. There's a multitude of different lengths that we have used throughout this class. Every length ratio is based on some kind of common length from one object to the other. It doesn't have to be necessarily a side length. When you look at area ratios, they might give you a surface area, a lateral area, or a area of a side. Those are all different ways they could give you a area ratio. Those ratios are they are consistent between those three types of areas. The last type of ratio they might give you is a volume ratio. Really, there's only one type of volume. So if they give you the volume of both objects, you know that they're starting off with the volume ratio. Second step is to convert it to the desired ratio. You're going to be looking to find something. Make sure you're using the ratio that goes along with the part that you're trying to find. If you're trying to find an area, use the area ratio. If you're trying to find a length, use the length ratio. And obviously, if you're trying to find volume, use the volume ratio. Third step is you're going to set up a proportion. And then your fourth step is you are going to do some cross multiplying and solve to find your missing value. So here's a good example of a problem you might see. Suppose the surface area of the larger prism is 2,560 square meters. Find the surface area of the smaller prism. As we look at this, they give us an area of the larger prism. Larger is important. And then they give you a bunch of measurements down on the bottom here. Now notice they give you 3 measurements. There's no question of whether these are similar objects or not. They tell you that they are similar. So we could go 20 and 12. We could go 22 with the 13.2. Or over here you could go 20 and 12 again. It doesn't matter which one you use. So I would pick the easiest one to work with. I like using this, putting the small measurement on the top, the larger one on the bottom. Just how I like to do my math here. So I'm going to take 2 sides. I'll take these 2 because they're pretty easy to work with. And we're going to find our scale factor or our length ratio. Our length ratio, because those are lengths, is going to be 12 over 20. Remember, our first step is always reduce that fraction. So I need to reduce 12 over 20. 4 goes into each of these. 12 divided by 4 is 3. 20 divided by 4 is 5. I have a length ratio that is 3 to 5. Now what I need to do is I need to convert that over to an area ratio. I usually put area over on the left. I moved it to the right. It doesn't matter. There's no rule that says going left you do this, going right you do this. You need to be able to convert between length and area accurately. Our conversion going from length to area is to square that length ratio. So if I square that ratio, that becomes 9 over 25. So that's the area ratio that I need to use. So I'm going to set up my proportion using the area ratio because I'm trying to find a missing area, find the surface area of the smaller prism. Notice I put my smaller measurement on the top and I put my larger measurement on the bottom. I'm going to set up my other proportion. This 2560 is a larger measurement. So that means the larger object was on the bottom. I'm going to go 2560 on the bottom. And I'm putting X up on the top. So if I do my cross multiplying now, 25 times X is 25X. 9 times 2,560 puts us at 23,040. We would need to divide both sides by 25. That puts us with an answer of 921.6. When you answer this question in Moodle, put the number in. Do not put the units in. The units are good to write down as you're showing your work. But in Moodle, it's looking for a numeric response. It will mark it wrong if you throw that in there. So please don't do that. All right. Here's a good example of a question where they're just asking for the ratio. If they're just asking for the ratio, there's really not a whole lot of solving going on. You're just converting from whatever ratio they start you off with to the ratio that they want. In this case, they want a volume ratio. We look down here at the information they give us in the picture. They give us a 2 lengths. So we're simply going to go 12 over 15. That's a length ratio. And we're going to convert that to a volume ratio. To convert to a volume ratio, we're going to cube it. Cubing 12 and 15, probably not the easiest in the world. Remember, before you start any problem, reduce. So that reduces down to 4 over 5. 4 to the third power is 64. That's 4 times 4, which is 16. 16 times 4 is 64. And 5 to the third power is 125. Now, I have been writing all my ratios like this. They're asking for you to write it in that form. It's just a different form of ratio. Don't let it throw you off. Top number goes first. Bottom number goes second. 64 to 125. And that's the answer we're looking for. These questions I added in. When I put these into the homework assignment, I was looking for some questions to really make you think about real-world applications of these similar solids. So they all talk about building a storage shed in the backyard, and they talk about different types of materials. Now, here's the deal. If you're talking about space inside a shed, that is talking volume. If you're talking about siding, or shingles, or other material that are covering surfaces, those are area measurements. And if they're talking about dimensions, like this one is, length, width, and height, that is a length ratio. Imagine that. It says length right there. So keep that in mind as you're going through these problems. So if we look at this specific problem, you're going to build a base that covers 4 times the area of the original plans. You want to keep the shed proportional to the original design, which means they're going to be similar objects or similar solids. What would you need to multiply the original dimensions by if you want the floor to be 4 times the area? 4 times the area, that tells you that they're giving you your area ratio, which is 4. What is your length ratio? Because we're trying to find the dimensions or the length. How do you convert from area to length? We square root it. So if we want 4 times the floor base, or the base, sorry, if you want to build a base that covers 4 times the area, that means you need to take your dimensions and double them all. That's going to give you that base that is 4 times the original area. These are the only problems that you're going to really need to do any volume or surface area type of formulas on them, are the problems that look like this right here. Now, they might not directly give you all the information you need, but you should have all the information required in order for you to find what you need here. So let's take a look here. You got use similar solids and their scale factors to find the volume. So we want volume ratio of the smaller cone. We want to find volume ratio and convert it so that we can have that smaller cone. So what ratio do I have here? So as I look here, I have a height of the big cone. I got this, which is really the distance between the circles. It's really not a measurement of the cones. It's maybe the distance between the 2 bases there. And this, which is the radius of the larger cone. Well, with this height of 15 and that distance there of 5, I know that the height of the small cone has to be 10, because 10 and 5 give me the 15. 10 and 5 10 plus 5 gives us 15. So my length ratio, or my scale factor, K is a symbol that sometimes means scale factor. We could go 10 over 15, which reduces to 2 over 5. So my length ratio is 2 over 5. I need to use that to create a volume ratio. So length ratio is 2 over 5. Convert that to a volume ratio. That means I'm going to cube it. 2 to the third power is 8. 5 to the third power is 125. That's the ratio I want to use for my proportion. So I'm going to set up my proportion. 8 over 125 equals, now here's where I come in, or I run into a problem. That problem is I don't have a volume to work from. So looking over here at my original diagram, I have enough information to find the volume of the larger cone. And once I find the volume of the larger cone, then I can plug that in, do my cross multiplying, because I know I need to find my x here, because that's where I'm going to put the volume of the smaller cone. So for volume of a cone, it is 1/3. That was supposed to be a 3. Pi r squared times the height. Oh, it's supposed to stay up there. There we go. So 1/3 pi times 8 squared times 15. You could type all that into the calculator and get your answer here. I'm going to manipulate this a little bit, just doing a little math. 1/3 of 15 is 5. 8 squared is 64. So that gives me 5 times 64, which is 320 times pi. I bet if you typed in that original equation, or that original information right there without the pi, you'd get 320. So I'm going to just pop that over here, leaving the pi involved. For those of you who have not left answers in terms of pi before, that's a great way of not having to round until you get to the final step, which makes your answer as accurate as possible. So we'll do some calculations now. So obviously, when we cross multiply here, that gives me 125x. And as I cross multiply here, that's going to give me 2,560 times pi. I just did the 320 times 8 for right now. So now I need to divide both sides by 125. And 2,560 pi divided by 125 puts us at 64.34. And putting these answers in the Moodle for your homework, I would say if it doesn't specify differently, round your answers to 1 or 2 decimal places. It should adjust. If you round a little different, than what I did, it should adjust pretty well. Then that would be your answer there. All right, last type of problem that I want to show you here, and it could be an argument that this should have probably been earlier in the lesson, But how do you determine whether two objects are similar, neither, or congruent to each other? Well, what you want to do here is you want to look at your ratios, your length ratios, that is. Simply take your similar parts. I got 4 to 6 there, taking small over large, and I'm going to compare that to the other lengths that I have, which here in this case, my heights, the true heights are 6 to 9. Now, if these ratios end up being the same, 4 to 6 reduces down to 2/3. 6 to 9 reduces down to 2/3. If they reduce to the same answer, that means they are similar. If they are different, that's when you would choose neither. Go different color there. If they were different, you would call it neither. If they were the exact same, meaning here, not the ratios, but the original lengths, if those original lengths were all the same, then they would be congruent because they're the exact same size. Now, a little bit of thought for you. Are congruent objects similar? The answer would be yes, because they have a 1-to-1 ratio. Are all similar objects congruent? The answer is no, because they can be different sizes. Congruent objects are similar. They just have a 1-to-1 ratio. That's okay. But similar objects are not always congruent because they can be different sizes. That's all I have for you. I will answer questions tomorrow. If you have questions, you can email me. But if you do email me, make sure you send me the question that you have. Take a picture of the question that you're working on, and send me your work so that I can help find where your sticking point is. All right. You guys have a great night. We'll talk to you tomorrow.